Okay, so we'll do one more quick example here, and this will be, more like what a student might do. You're not going to do all those ones like I did at the beginning. So there you go, I have it written, and then there's my line. It's going to be where my repeated subtraction numbers are going to go. Okay, so again, I'm going to use numbers that I'm comfortable with, whatever the student is comfortable with. So I'm not real good with multiplying my 27s, but I know that if I'm going to get to 3,600, that I could go 27 times 100, and that's going to be less than 3,600. So 27 times 100 is 2,700, just like that. And then I'm going to subtract, and I get 1, 5, and 9. Okay. So then I go, well, I don't really know what my, 27 times what gives me 950. So I might just go times 20, right? So I don't really know, but 2 I think is 54, so I could go times 20 would be 540. And maybe they do a little side problem over here of 27 times 2, whatever. I'm fine with that. And so then we're going to go here and we get 4, 1, 1. All right. So now I definitely don't know 20 won't fit. So I'm probably going to do 10. So then that is 270. So that's 1, 4, 1, 141. Now I might do 5, right? Because I don't, obviously 10 won't fit. I don't know 5 times 27, so I'll do 27 times 5. That's 135, so 135. Subtract those. I don't know why I kept using the same color. And then I get 6 here. So now I can add these up and get my answer. So I got 100, 120, 130, 135. That's 135. And then I still have the issue with that 6 going on the top and the 27 on the bottom. But at least over here, I got to use numbers that I was totally comfortable with. Okay, so that is a second example of repeated subtraction. And now I'm going to pause it, and I'm going to do a different type of algorithm for division. Okay, so for this algorithm, we're going to go back to that very first problem that we did at the beginning, 872 divided by 6. And the very first issue that I said with this is getting kids to learn how to write it, right? How do they know what goes inside and what goes outside? And like I said before, students automatically think the big number goes inside, the little number goes outside, because that's what they're used to doing from the very beginning. But it doesn't have to be that way. We know that you very well could be dividing a big number into a little number. So it doesn't have to go that way. So the first thing, one reason I came up, this strategy here, you're not going to find in the book. I kind of formulated this over a couple of years to solve some problems that I was having. And it helps solve that problem right there, because I get to write this exactly the way I read it. So I read this as 872. So I write that as 872, and then that symbol is divided by, so I write in my divided by symbol, and that number is 6, and that's 6. So there we go. I have 872 divided by 6, and this is 872 divided by 6. So that's the first thing that I like, is that it no longer caused an issue with how do you write it. Kids didn't have to remember inside, outside, any of that junk. They just rewrote it. Okay. Now I call this upwards division. And so what you're going to see here is it's very similar to the traditional algorithm. So I taught this because I was teaching 8th graders, and they were working about a 4th grade level, and those students were very bad at long division. They could remember the process, they could do a bunch of the steps right, but a lot of that what they do with the remainder was the problem. So it goes frustrating. After a while, I got frustrated because I kept trying to teach them the same way other teachers had been teaching. But they saw that in 4th grade, then again in 5th grade, and then 6th, then 7th, and I get them in 8th grade. I can't teach them how to do that. I'm not a better teacher than their other teachers were. So I came up with a different way, something that would help solve that issue at the end, and that's what this is. So these students are pretty good at doing our algorithm, right? They can do our traditional algorithm. It's just they don't really know what to do at the end. So I'm going to use that same idea of the algorithm. 6 goes into 8. 6 goes into 8 one time, okay? And then 1 times 6. 1 times 6 equals 6. And I put that right up here. Notice that I spread these out when I wrote them. I did that on purpose. So now I have 8 minus 6. So 8 minus 6 equals 2. That 2 goes right here. And now this number is 27. So 6 goes into 27 4 times, just like our other algorithm. 4 times 6 is 24. So I go 27 minus 24 equals, and that equals 3. That 3 goes right here. And so then I have 6 goes into 32 5 times. 5 times 6 is 30. And 32 minus 30 equals 2. Okay? So that's not that much different than what we did over here, right? We still got 145. I still got 145. The process is basically the same. What's different is right now. Now I have to do something with that remainder. And my issue with this was students didn't know what to do with the remainder. Like they had no idea. They did all this crazy stuff down here. So now what they see is that, hey, holy cow, look at this. This remainder is already on the top. So it stays on the top. That's a 2. And what's the denominator? Well, the denominator is that 6. So it's 2/6, just like that. So 145 and 2/6. So the beauty of it is not so much this part, right? This is still kind of hectic and they got to be good at subtracting kind of, you know. I'll show you another problem. I used to have my students, my PAR students, my low students, they actually could do these in their head faster than my algebra kids could do them because I taught them this and they could actually do a lot of these in their head. And I'll show you an example of that in just a minute. Not quite as complicated as this one. This certainly they'd have to write on paper, but a lot of them they could do in their head. And so the beauty of it is at the very end, this 2 is my remainder and that's my numerator. And the only denominator I've had the whole time is the 6 and that stays my denominator. So now let's take a look at a problem that students might be able to do in their head once they get good at this. So that might be something that looks like this. 58 divided by 9. Okay, so 58 divided by 9. Most of us probably would set that system up, you know, that long division up, but my students in their head, they would think, okay, 58 divided by 9. So how many times does 9 go into 58? Well, 9 goes into 58 6 times. That's 54. So that means there's 4 left over. So 4 ninths, 6 and 4 ninths, just like that. And they wouldn't write any of this down. They would just look at 58 divided by 9, and you go, well, that's 9 times 6 is 54. There's 4 left over, 4 ninths, just like that. So I like to teach this upwards division. Oh, by the way, I call this upwards division. I don't know if I mentioned that. You're not going to see this in the book again, and I like it just because it solves a couple of problems. One problem is they get to write it as they read it. So 872 divided by 6, 872 divided by 6, and then it also solves this issue at the end. I agree that this is not awesome, and some students are not great at this subtraction here, but this is a trade-off for the end because a lot of kids struggle with what to do with that remainder. And then they can do a lot of these problems in their head. More simple problems they can do in their head because they already know, okay, 9 is going to go into that number 2 times or whatever, and my remainder is going to be 6, and so whatever. So it's kind of nice. They can actually get a lot of these done in their head. Okay, so that's division.